So far in this course, we've been looking at a few examples of what we call macroscopic physics laws, like Gauss's law, where we're looking at the flux of an electric field through a closed surface. And we compared that to a physical quantity that was enclosed. And in this case, well, in our units, we have a constant. And we compared that to the charge density enclosed in that region of space. We've sometimes called that a volume integral. And this is an example of looking at a region of space and comparing something on the surface, the flux of electric field, to something that's integrated over the volume of space. And if we took a little volume dV and we have a charge enclosed in that volume and adding that up, so we're comparing a surface integral to a volume integral. Now, in mathematics, there's some theoretical results called the divergence theorem. And the divergence theorem makes the statement that a closed surface integral is equal to the divergence of that vector field integrated over the volume. So once again, we have a closed surface, and we have a volume enclosed. This again, here I could make 3 signs for the volume. That's the enclosed volume. And this mathematical result and our physical law, we can now equate the two sides, and we see that using the divergence theorem, that the divergence of a vector field integrated over a volume has to be equal to the integral of the charge enclosed in that volume. So this is both sides are now volumes in 3-dimensional space. And of course, we have our constant. And what we see now is we can now go from these integrals over surfaces and volumes to asking ourselves, what would happen if we shrink our volume down to just a point contained in that volume? Well, if that's the case, and these integral results hold over the volume, as we shrink it down to the point that's inside the volume, then the integrands must be equal, and that enables us to write an equation, del dot E equals charge density divided by epsilon naught. And this holds at all points in space. And so what we now have is, instead of talking about a macroscopic law involving closed surfaces and volumes, we're shrinking our closed surface down to essentially a point that's contained in it, and we have a differential relationship that is governing the divergence of the electric field at any given point compared to the charge density at that point. And this is an example of a differential version of Gauss's law. So our last example of using the divergence theorem in electromagnetism will be with magnetic fields when the vector C is the magnetic field. Now, our law is that magnetic flux is conserved. That means that there's our global Maxwell equation, that whatever magnetic flux comes into a closed surface has to be equal to the flux going out of that closed surface. And so when we now apply the divergence theorem to that case, it's very straightforward that the divergence of the magnetic field is always 0 at every point in space. And so let's just summarize our 2 Maxwell equations in differential form. We have conservation of magnetic flux. Our electric flux is not conserved because point charges are sources of electric flux. So if you have a positive charge, the electric field goes away, a negative charge, electric field goes towards, and our differential equation there is 1 over epsilon naught times the charge density at every point in space. And so these are our two Maxwell's equations in differential form.